Today we'll solve trigonometric equations. Let's do a little review of a quadratic first. It's already set equal to 0. If it wasn't, we want to do that first. Then we take, obviously, in factors. So I've got a 2x here. An x, I need a 3. It's got to be the positive, and a 1, which is the negative. So I set them both equal to 0. And x equals 1/2 and -3. Pretty basic. The idea behind solving trigonometric equations is not much different when it looks like a quadratic, as this does. Except you'll notice instead of just an x, it's the cosine of x that's being squared. Now, we're going to solve for all values between 0 and 2 pi. So if I look at this, it's a quadratic. We're going to factor. That's the cosine of x times the cosine of x. And then that's set equal to 0. I need a 4. It's got to be my negative. I need a 3, or I need a 1, sorry. And that's got to be the positive. So I have the cosine of x is equal to -1, and the cosine of x is equal to 4. And when we were solving quadratic equations, we'd be done right now, but we're trying to solve for x. So we have to take the inverse of both sides. And you'll notice this has a unique solution, whereas the x value, -1, that's only going to be at one place, that's at pi. And then where is the x value going to be 4? This is never going to exist, because if you look at a cosine function, it goes between 1 and -1, or a sine function, however you want to look at it. There's your cosine function. All right. And so this has an extraneous solution part to it. So our answer is strictly pi. Now in this case, you'll notice there's not a quadratic, but if we're going to solve it like we would an equation, we can set aside equal to 0. So I have sine of x, tan of x, minus 3 sine of x is equal to 0. And then we notice we have a common term of sine. So I'll pull that out and have the following. So now you'll notice we go about the same process as we did last time. Sine is equal to 0. Tan is equal to 3. And we can find the inverses again. Say x is equal to the inverse sine of 0. And x is equal to the inverse tan of 3. Now in this case, you're going to notice something different. We take the inverse sine of 0 and find out where is the y value actually equal to 0. Well, that's at 0 and at pi. And tangent, we can actually answer this, except we can't like pull it out of thin air like we just did for the sine, because tangent looks something like this and we have no idea where it's equal to 3. So we're going to need a calculator to do it. And really all you have to do is put that calculator in the radian mode, take the inverse tangent of 3, and you'll come out with a value of 1.249, let's say, and that's in radians. Now, the question is that 1.249 the only value? Well, between 0 and 2 pi, probably not, because we know tangent normally looks like this. And that's at pi, but then again, it continues to go up again until I get to 3 pi over 2. So it's going to hit 3 twice. So really what I have to do is I have to say not only is it 1.249, but it's 1.249 plus pi, or 3.14. And if I add that to 1.29, I end up with 4.389. So there's 2 values of that tangent. So you'll notice in this problem we have 2 different trig functions. Neither one's in common, so that's a little bit different. We know we could factor this actually. I prefer to kind of have the same function if at all possible in my problems. And I'll show you a way around it in a second. The other important thing I want you to notice is the problem's changed in what it's asking for. It's asked to find all values of x for which this is true. And we'll get to that in a minute, but let's solve this first. I'm going to like I said, I want to make one function, which I can do with the Pythagorean identity, but in this case I'm going to do it a little differently. I'll bring the cosine squared to the other side and then divide by the cosine squared, which gets me a sine squared over cosine squared, which is tangent squared of x is equal to 1. So then I square root both sides and get tangent is equal to plus or minus 1. And I want to know everywhere that tangent is equal to plus or minus 1. Well, it's equal in these 4 places, which are all portions of pi's over 4s. But I can also say this, that if I know this is like 90, 135, 225, and 315, each pair of these has a relationship that is 180 degrees apart. So what I could do is I could say, well, I've got pi over 4 plus pi n, which is all in multiples. Then I can say 3 pi over 4 plus pi n again, and then I have all multiples here. So we're going to use multiples of, or n multiples of some number on pretty much anything that's going to have all values of x, like this problem. And we've done something similar to this before. We're going to take and factor. Got a 2 tan x and a tan x. Got a 5 and a 3. We'll go negative here and a positive here. This is tan of x is equal to 3 halves, and tan of x is equal to 5. These are both going to be calculator style problems. Let's just put a circle right here to look at where we land. All right. When we take the inverse tangent of 3 halves, we get x equals roughly 0.98. And these are in radians again. And then we take the inverse tangent of 5, we get roughly x equaling 1.37. And these are in radians again. I could put them in degrees, but I'm going to put them in radians. So now, where are these going to be? 0.9 radians is probably somewhere around here. You can convert that to degrees if you'd like. And 1.3 is just short of pi over 2, right around here. So we know, granted, that these values are truly answers for the equation, but also, too, they're symmetric points on the other side of the equation, or other side of the circle, just like in the last problem, happen to be solutions as well. So to each of these, we're going to have to add multiples of pi. So basically, if we take 0.98 plus pi n and 1.37 plus pi n, we get all values. We're back to finding answers between 0 and 2 pi. Now you'll notice in this case, I've talked about it a little bit before, I'd like to get either common terms, which I'm not going to get here, or I'd like to get the same trigonometric function throughout the problem. And I don't have that right now, but I can get it because I know I have a Pythagorean identity for tangent squared. So I know that 2 times secant squared minus 1 is equal to tangent squared. And now notice I've turned the problem from 2 different functions into one function. So I have basically 2 secant squared of x minus 2 plus 1 is minus 1 equals secant of x. Set aside equal to 0. Factor. We'll have a negative on this guy right here and a positive on this guy. So I get the secant of x is equal to negative 1/2. And the secant of x is equal to 1. Now I'm not very good with secants at all. So what I'm going to do is I'm going to change my secants to cosine by taking the reciprocal of both sides. So if I take the reciprocal and say, well, this is going to be cosine cosine is not equal to negative 1/2. Cosine is equal to negative 2. And then I'm going to again take the reciprocal of here, and I get the cosine of x. Reciprocal of 1 is 1. Now I can tell a little bit about the values. I know the value here is not possible because cosine goes between 1 and negative 1. And I know the value here, whereas cosine equal to 1, that's the x value, and that's only going to happen at 0 degrees or 0 radians, either way. This last problem is going to be a little bit difficult because of this 3 right here. Now, the big thing to notice is this 3 indicates a period change. So basically, I know that the period of this sine function is 2 pi over 3. All right, so what that means is it means that this will happen all in this amount of time. And if I want answers between 0 and 2 pi, then I'm probably going to have 3 portions of my solution happening. So if I add 2 pi over 3 to the final value, I'm going to get another appearance of that. It's not quite the symmetry that we've talked about before in terms of a unit circle, but because I know the period of this function is happening every 2 pi over 3, then I know that every 2 pi over 3, another occurrence of an answer is going to happen. And I'll show you how that plays in a minute. I know the sine of 3x is equal to negative half. So I'll take the inverse sine of negative 1/2. This I can answer pretty readily. I know that where is my y value going to equal negative half? It's going to be somewhere down in the 4th quadrant and the 3rd quadrant. So in that case, I know that the y value is going to be at 11 pi over 6 and also at 7 pi over 6. And those values are going to equal 3x. X then would equal 7 pi over 18, and x would equal 11 pi over 18, which those two answers are in this area of the circle here because they're before pi. So now I know if I take and add 2 pi over 3 to these, and in this case I'm going to change 2 pi over 3 into 18ths, so that means if I multiply each by 6, 12 pi over 18, if I add 12 pi over 18 to these, I'll get new answers. So if I add 12 to this, I get 19 pi over 18, and that's still within the 2 pi range. If I add 12 again, notice what I'm going to get. I'm going to get 27 pi over 18, which is still less than 2 pi. If I add 12 again, I'm going to be over 2 pi, so I'm done. In this case, I add, once again, 12 to that, and I get 23 pi over 18. I'm still not over 2 pi yet. If I add 12 again, I'll get 35 pi over 18, which is still less than 2 pi. So for this problem, I have 8 answers, which kind of makes sense. In my initial explanation, I said it's going to happen twice here, and here's another 2 pi over 3, and here's another 2 pi over 3. So there's my 6 answers within the unit circle. And that's all we've got for today. Until next time.